Welcome to Distributed System course. In the previous session, we discussed Mikawa's algorithm for mutual exclusion in distributed system. Today, we are going to discuss another algorithm, that is Suzuki-Kasami broadcast algorithm. We have to achieve mutual exclusion among a collection of processes so as to coordinate their actions, that is access to the shared resource. That is, the only one process is allowed to execute the critical section at any given instant of time. The action performed by user on shared resource must be atomic, but in the case of distributed system, we neither have shared memory nor a common physical clock, and therefore we cannot solve the mutual exclusion problem using shared variables such as the semaphore and other clock problems. To eliminate the mutual exclusion problems in distributed system, we are using message passing. We already see some of the distributed mutual exclusion algorithm for distributed system. Some of them are the Lambert's logical clock algorithm, then Ricard-Agarwal algorithm, then Mikawa's algorithm, and Suzuki broadcast algorithm. In the previous sessions, we discussed the Lambert's and Ricard-Agarwal and Mikawa's algorithms. Today, we are going to discuss the Suzuki-Kasami broadcast algorithm. In the Lambert's algorithm and the Ricard-Agarwal algorithms are non-token based algorithm, and Mikawa's algorithm is a quorum based approach. First, we will discuss the systems model. The system consists of n sites, that is S1, S2 and Sn. We assume that a single process is running on each site. The process site SA is denoted by PA. A site can be in one of the three states, that is, first one is the requesting the critical session, executing the critical session, and the neither requesting nor executing the critical section. In the requesting the critical session state, the site is blocked and cannot make further request for critical section. In the ideal state, the site is executing outside the critical section. At any instance, a site may have several pending requests for critical session. A site queue up these requests and serve them one at a time. Then come to the Suzuki-Kasami algorithm. It is a token-based algorithm for achieving the mutual exclusion in distributed system. Suzuki-Kasami algorithm is a modification, that is, we are changing some of the properties of Ricard-Agarwal algorithm, then we will get the Suzuki-Kasami algorithm. But the Suzuki-Kasami algorithm is fully based on the token, but in the case of Ricard-Agarwal algorithm is a non-token based algorithm. In non-token based algorithm, we can say that it is a permission based algorithm. That is, in which we use the request reply messages to ensure the mutual exclusion. But in the case of non-token based, token based algorithm, we are using a token to ensure the mutual exclusion properties in distributed system. The non-token based algorithm uses a timestamp to order the request for the critical sections. We already see the timestamp. By using the logical timestamp, we are ordered the messages or request for enter in the critical session. But in the case of token based algorithm, we are using sequence number for the ordering of the critical session requests. So in token based algorithm, a site is allowed to enter its critical session if it possesses the unique token. First, we will discuss the data structures and notations used in the particular Suzuki-Kasami algorithm. The first data structure is one token. Then it contains two parts. That is, first one is a queue and an integer array. The queue is used to keep the record of IDs of sites waiting for the tokens. So in each and every process or site contains an ID. we use the queue to store the record of IDs of sites waiting for the tokens. Then the second part of the this token is one of the array, integer array. It is denoted by ln. The size of this it is varies from 1 to n. The sequence number which is used by the token which is used to which contains which keep track the sequence number of the request that is recently executed by site SI. So the token contain two part, the queue and an integer array. Queue is used to store the IDs of the site waiting for the queue. The second part, the integer array is used for the sequence number of the request that is recently executed by particular site SJ. So it contains the ln is an integer array which is the size of the number of processes. The size of the array is equal to the size of the number of processes in the system. The next part of our next data structure in this is the request message. The request message contains also two parts. That is, first one is it contains two parameter. First one is I and second one is k. The request message from node I for its kth critical section execution. That is, it contains an ID. First of all, the request contains an ID that is represented by I. That is, if a particular process SI that is requesting to enter the critical session for its kth critical session execution, then the request message will contains the two parameter I and k. The I denote the requested process ID and the k is the kth critical session. The other data structure used in the Suzuki-Kasami algorithm is another array that is denoted by request array, that is Rn, which is store the latest sequence numbers received so far by particular process I in request message from site SJ. That is used to store the latest sequence number of all the process. It maintain an array that is called request array. That is an integer array. That is the size of it is also based on the number of sites or process in the system. So we have a token consists of two parts, a particular queue and a integer array. Integer array is used to store the sequence number of the request that is recently executed by a particular site. Then the second data structure, which is a request array, that is it also store the largest sequence number received by the particular process from another process. And we are also sending the request message which have two parts, the ID and the kth critical sections. That is about the data structures of the Suzuki-Kasami algorithm. Then the basic idea of this Suzuki-Kasami algorithm is, if a site wants to enter the critical session and it does not have the token, it broadcasts a request message for the token to all other sites. A site which possesses the token sends it to the requesting site upon the receipt of its request message. Then after sending the token, a particular site receives the request message. When it is executing the critical session, it sends the token only after it has completed the critical session of the that particular process. That is the idea. That is, if a particular site wants to enter the critical session, it is send a request message containing its ID and the nth and the kth request to the particular all other sites in the system. When a site which possesses the token send it to the requesting site upon receipt of the request from that particular process. If a site receive a request message when it is executing the critical session, it is sent only after the completion of the critical session. That is the idea of Suzuki Kasami algorithm. Then come to the algorithm. Before come to the algorithm, there are the design issues. The first one is how to distinguish an outdated request message from a current request message. That is a first design issue. That is how to distinguish an outdated request message from a current request message. That is, if there's another design issue is how to determine which site has a outstanding request for the critical session. That is a second design issue. There are two design issue. First one is how to distinguish an outdated request message from a current request message. The second one is how to determine which site has an outstanding request for the critical session. We will first note down the design issues. That is, due to the variation, first design issue is how to distinguish an outdated request message from a current request message. The problem is, due to the variable message delay, a site may receive a token request message after the corresponding request has been satisfied. If you consider a particular system contains two processes P1 and P2, the P1 P1 want to enter the critical session, it does not have the token, so it is sent the request to another process P2, which the request message contains two parts, that is its ID, P1's ID is 1, and the its corresponding time is, that is it is 2 is sent to the process P2. So on receiving the request message from P1, P2 can identify that it request message contains the timestamp 2. At the same time, it has the timestamp 3. So it is a old message. So we will it is a outdated message. The solution to this particular problem can be avoided by using that is a request message of site Sj has the form, that is a request of Jn, where n is a sequence number indicate that the site Sj is representing its nth critical section. A site Sj keep an array of integer, that is a request array, where r of nij denote the largest sequence number received in the request message so far from site j. When site Sj receive a request j comma n message, it is set r n of j to max of this value. So this is one of the solution. That is, if we get two messages in different values, then we will take the maximum of it, then we will set it to the value as the request array. When a site Si receive a request message j comma n message, the request is outdated if the value, that is the value in particular Rn of j is greater than n. That is a case, that is example here. That we receive a message with 2, that is n equal to 2, but in the case of already the process P2 contains a particular request array entry as 3. So it is an outdated message. This is how we are solving the first design issue. The second design issue is how to determine which site has an outstanding request for the critical session. This can be solved by the token consists of a queue of for requesting site and an array of integers, that is ln, that is used to store sequence of the request which is Sj executed most recently, or we can say that it is a latest sequence number that is executed by the particular process. After executing its critical session, the site Sj update ln of j to Rn of j to indicate that its corresponding to sequence number has been executed. That is the idea. So we can identify the outstanding request by this way. After executing its critical session, a site will set its value to the requesting array 2 is copied to this particular latest value of this particular array. At this site Si, Rn of j equal to ln of j plus 1, the site Si is currently requesting the token. Suzuki-Kasami algorithm. The algorithm contains three parts. First one is the requesting the critical session. Then second one is if the requesting site. Then second part is executing the critical session. The third part is requesting the critical session. First, we will discuss the requesting the critical session part. If the requesting site SA does not have the token, then it increment its sequence number and the corresponding value in the request array and send a request message to all other sites. When a site SJ receives this message, it set the request array entry to maximum of the particular values, that is current request array values and maximum of current request value and the particular sequence number in the message. Then if SJ has the ideal token, then it is sent the token to SA. So upon receiving a particular message, it will send the token if it has an ideal token. Otherwise, it will send only after the execution of the critical session. Then second part is the executing the critical session. Site SA execute the critical session after it has received the token. Then third part is the requesting releasing the critical session. That is, it is set after executing the critical session, it is set the value of the ln of I element of the token array to the corresponding request array. For every site SJ, the whole whose ID is not in the token queue, it append its ID to the token queue. That is, it will append the queue if the corresponding condition is satisfied. That is, if Rn of phi j equal to ln of j plus 1. The token queue is a if the token queue is non-empty, after the above update, the SA delete the top site ID from the token queue and send the token to the site indicated by the ID. Consider a particular system consists of the four processes, that is P1, P2, P3 and P4. Then it will first set all the requesting array to 0. Then if a particular token is handled by P2, initially it is in the handled by P2. So it contains two part Q and ln. The Q is empty and ln equal to 0. Then at the same time, the P1 want to enter the critical session, so it will send the request message to P2. Then after P2, it will send the request message to P2, P3 and P4. So the P2, P3 and P4 will update its the request array to 1, 1, 1. Then after the particular token is hand over to this P1. So P1 can get the token. So P1 can enter the critical session. Then after P1 enter the critical session, it updates the ln value to 1. Then here the queue is empty. No one is waiting in the queue. Then it will at the same time P3 is sending the request message to all other message to enter the critical session after updating its the request array to 1. Then after that all the process the updates its request array to 1. Then the P1 will send the token to particular process P3. Then P3 can enter the critical session. During the critical session execution of P3, P2 and P4 want to enter the critical session, so they will send the request to it. The request cannot be handled because the P3 is in the critical session. So after the execution of the critical section, then it will update its queue based on the ln value. That is, it will update the ln value to P2 is P2 and P4 it is in the queue. Then it will take an element, that first element from the queue, and it is send that token to that particular process P2. After receiving the P2, P2 can enter the critical session. Then after execution, it will update its ln value and it will send the token to the next process in the queue, that is P4. After executing the P4, the token is in with the P4. Then the particular process P1 want to enter the critical session, it will send request message to all other process, so P1 can enter the queue after enter the critical session after receiving it. So the queue will become empty. So this is how the particular process is executing the critical section. The it is satisfy the mutual exclusion, also it is satisfy the liveness properties and fairness of this. Come to the message complexity. The message complexity is it needs 0 to n minus 1 request and 0 to 1 reply. So the total is 0 to n minus messages per critical session. Synchronization delay is 0 to t. Thank you.